So today's a really cool topic. It's about something called the Lovász Local lemma and an accompanying algorithm called the resampling algorithm. So, okay, so we're actually going to, among other applications, we're going to focus on SAT. So that goes all the way back from lecture one. Here is a quick rewind through all the things we did. I guess I don't need to remind you in light of the recent midterm. So here now is today. I guess the sort of mathematical, probabilistic portion will be about this thing called the local lemma. But we'll also have an algorithm for it due to Moser, and it's actually not that old. It's only from 2009. Also, Moser was a graduate student when he came up with it, not to put too much pressure on you guys. Okay, so first let me just set up 3SAT, or KSAT in general. This was from the first lecture, but we're just looking at, CNF formulas that have k variables per clause, and I want to know if I can satisfy all of them. For sake of approximation, we looked at also maxsat. We're trying to satisfy as many clauses as possible, where, for example, for 3SAT, we saw that every clause is satisfied with probability 7/8, but in general for KSAT, every clause is satisfied with probability 1 minus 1/2 to the k, right? Okay, so for example, all right, so here's maybe a funny way to look at it. So let's say I gave you a KSAT formula. So k clauses, k variables per clause, okay? But suppose there wasn't that many clauses. Suppose the number of clauses was less than 2 to the k, okay? All right, so now let's look at a random assignment like we've always analyzed. A completely random assignment to a KSAT formula where the number of clauses is less than 2 to the k. Okay. I want to try to argue, well, we'll see. All right, so I've started with, okay, what are the odds that this formula, when I plug in a random assignment, is false? And I want to get an upper bound on this. Okay. What's maybe one step to try to get a sort of lazy upper bound? This won't be a very tight analysis. Yeah. Yeah, so we'll do something simple. We're just going to take a union bound over all the clauses, right? Okay, so I'm summing over all the clauses. What are the odds that the ith clause is unsatisfied? Okay. And if it's KSAT, then what is the odds that the ith clause is unsatisfied? What are the odds for KSAT? 1/2 to the k. Okay. So we get m/2 to the k, which in this particular scenario is at most 1. Okay. So if the number of clauses is less than 2 to the k, then actually a random assignment, the odds of it evaluating to false is less than 1. Okay. What does that say about f? It is what? It must be satisfiable. Okay, if the odds are less than 1, then the odds of also satisfying f are greater than 0. So there is a satisfying assignment. Okay, so very simple argument. But if m is really small compared to k, or in particular 2 to the k, then f must be satisfiable without knowing anything about the structure of f. Okay, here I'm assuming there's no like clauses that are like obviously impossible, like x1 or not x. Oh no, that's fine. Ignore that comment. Okay, okay, fine. Now that's a very simple argument, of course, and it only works for this very simple case where m is smaller than 2 to the k. If m is bigger than 2 to the k, then the union bound is not strong enough, and we're back to the old situation. Okay. All right. So here's an algorithm we're going to analyze. A very simple algorithm, one that maybe you would have tried if you were just trying to come up with some heuristics to solve KSAT. Okay. So the first step is going to be the same. I'll start with a completely random initial assignment. Okay, so x1 through xn is completely random, true, false. Okay. And then if you satisfy your clause F, then you're done, right? Great, you win. But otherwise, maybe there's some unsatisfied clauses. So we're going to pick one of them, and that's going to have some variables in it. It's going to have k variables in them, and I'm going to resample all of them independently. So those k variables, I flip new k coins for them. That gives new true false assignment. If I'm lucky, maybe that was the last clause that needed to be satisfied and I'm done or something. But maybe I'm unlucky, maybe that ruins some other clauses, so on and so forth. Okay, so the algorithm is just going to repeatedly pick an unsatisfied clause, resample unsatisfied clause. Okay, if it can't find an unsatisfied clause, then great, we win. We've satisfied the assignment. We'll return the current values of x1 through xn. But of course, the algorithm might not terminate. Okay, but the algorithm is very simple, right? It's like barely more complicated than our original algorithm, which was just to randomly assign everything. Okay. All right. So here then is sort of the an interesting theorem. So, okay. So we're going to be looking at formulas that may be very big. Okay. So we're really interested in the case where m is big, because if m is less than 2 to the k, we're already done. Okay. But we're going to assume that sort of has some limited notion of complexity. Okay. So let's say that every clause in the formula shares a variable with at most d other clauses. Okay, so I mean d could be as big as m, and then all the clauses are like intersecting with each other, and that's a lot. But if d is small, and in some way there's some kind of limited amount of connections amongst the clauses. Okay, so if d was 0, then the clauses would be completely separate. That would be very easy to satisfy. And d equals 1 maybe would be something clever with breadth first search or something. I don't know. Right? It wouldn't be surprising if maybe d equals 2 could be like a undergraduate problem or something. In any case, the theorem is, okay, if d is at most roughly 2 to the k, so 2 to the k over e minus 1, okay, then we have the following surprising claims. First, f is satisfiable, no matter what. It just is. Okay, so if this parameter d is sort of like the depth in some sense of the formula is smaller than roughly 2 to the k, then f is automatically satisfiable. Okay. All right. Fine, it's satisfiable, and then here's the other one. That silly algorithm we just discussed is actually going to find an assignment. It's a randomized algorithm, so who knows how long it'll take, but the expected amount of time can be bounded by saying that, each of these clauses is going to be resampled 1 over d times an expectation. So actually less than 1 for every clause. Okay, so you're kind of hoping, I guess that suggests that your initial sample might already satisfy a lot of clauses and you won't have to fix too many times. Okay, so this is, given how daunting SAT is in general, this is quite a strong theorem. Says that f is satisfiable, and a very, very simple algorithm can find a satisfying assignment. Okay, does the claim make sense? All right. So, okay, let me point out some features. So, the main property where we're just figuring out, how many times each clause intersects with other clauses is a very local feature. You don't even really have to look at the whole formula in some ways to inspect it. For one clause, you just look at the neighboring clauses, so to speak, where a neighboring clause is one that shares a variable. Now, the first statement, which is sort of more of a mathematical statement, not an algorithmic statement, has been known since the 1970s, was this introduction of this Lovász Local lemma, which I'll explain in a moment. But for many years, uh, we knew that such formulas were satisfiable. We didn't know how to get satisfying assignments. So people started maybe working on this in like the 1970s or 1990s or so. In 1991, there's a result saying if d is at most like 2 to the k divided by 50 or something, right? So off by a lot, but at least it's something. And then there's sort of incremental progress for about 20 years. And it was only in 2009 when we found out that that very simple algorithm will actually get this very strong bound. So this bound is also tight. Okay. It's pretty exciting as far as theory goes. Okay. All right. So this being able to satisfy K-SAT formulas with limited dependencies is really a specific case of a more general phenomena. It's called the Lovász Local lemma because it was introduced in a paper by Erdős and Lovász in 1975, and Erdős always credited to Lovász. Okay. So the more general setup is as follows. We're studying like a family of events in some fixed probability space. Okay, so I'm just denoting them A1 through AN. Okay, so if we were talking about K-SAT, then the ith event might be the event that the ith clause is unsatisfied. Okay, and we're looking at events. Well, we're going to be studying sort of what happens when the events are, not all completely dependent on each other. They have maybe there's some dependencies, but it's somewhat limited. Okay, so in the same sense that we were sort of keeping track of how many clauses one clause overlapped with. We were also going to maybe limit, each event, how many other events are sort of not independent from it. Okay, so I'll write AI tilde AJ to mean that they're not independent. Okay, so the high level question is, is it possible, is there some non-zero chance that none of the events occur? So for K-SAT, is it possible that none of the clauses are unsatisfied, which means the whole formula is satisfied? Okay, that's the high level question. Okay, so, all right, as a warm up then, what if A1 through AN were independent? I'm asking you guys. What if A1, assume that all the events have some probability strictly between 0 and 1, so there's some chance of it happening and some chance of it not happening. What if all the events were independent? What would we say about this question? Yeah. Okay, why? Okay, so the probability of kind of all of these events not happening uh, would become the product of each one, which, assuming each of them is at least 0, will give you something non-zero. Okay, so that's one case. Okay, now what if the events, we didn't assume anything about the dependence among the events? Okay, yeah, it depends. Well, okay, so if A1 was the complement of A2, then it would be impossible for none of them to occur, right? As soon as A1 doesn't occur, A2 occurs and vice versa. So, yeah, so you need some kind of assumptions to be able to state in any kind of absolute terms that the probabilities are going to be greater than 0. Okay. All right, so here then is sort of the technical version that will prove that Erdős and Lovász introduced, and then there'll be a friendlier version coming up that'll be easier to apply to KSAT. But let me walk through this slowly. Okay, so again, there's these events. Okay, so it says that suppose somehow you can come up with some sort of values, xa1, xa2, these x values for every event that satisfies sort of this eccentric inequality. The probability of the ith event occurring is at most xai times the product over all other events that are not independent from ai. So this would be like all the overlapping clauses and stuff like that. Okay, but not including ai. 1 minus x aj. Okay, so if you have these magical values, if they exist, you don't actually have to construct them if they just existed. Then, remarkably, the probability is guaranteed to be greater than 0. Okay, sort of technical at this stage, but it is what it is. If there exist these values x that satisfy this inequality, then it is possible for none of the events to occur. Okay? The strength of this statement is that, well, we make some assumptions on the a's, on the events, right? Because we know that these x's corresponding with this sort of neighborhood or incidence structure satisfy this inequality. But still, there could be a lot of things going on with the events, right? It could be from some very complicated graph coloring or SAT formula or other combinatorial setting. There could be a lot going on with those AIs. And given or compared to the complexity of these combinatorial problems, this is a relatively simple criteria that hides some of these things, some of these details. So maybe it'll be more compelling to do a friendlier version. This is sometimes called the symmetric local lemma. All right, so let's say that each event is independent from all but d other events. So d is just like before. Okay, and suppose that all of the events are bounded above by p. Okay. If e times p times d plus 1 is at most 1, then it's possible for all the events to occur. Okay, so maybe a better one is, if you wrote that if d is less than 1 over e times p minus 1, then it's possible for none of the events to occur. Okay. So this much simpler version will follow from the complicated version by just setting xai to be 1 over d plus 1 for all ai, and then just checking that it does work. Okay. In the case of KSAT, the odds of a formula of a clause not being satisfied was 2 to the k, okay, which is how we got this bound of d is at most 2 to the k over p minus 1. Okay. Okay, so we're focusing on KSAT partly because we've done it before, partly because I ran out of time. But I should mention there's just many other applications of local lemma out there, problems ranging from routing to, it's really a big deal in like mathematics and graph theory, like making extremal graphs and colorings and stuff like that. I'll think of some exercises to explore this space. Okay, so it's much broader than just the KSAT that I'm presenting here. Okay. All right. Questions? Yeah. 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 I'm sure it's not the only typo. That's what you meant? Okay. Other typos? Rightos? Whatever. Okay. Fine. Okay, so our discussion only really addressed the fact that f is satisfiable to this point. there's this other issue of actually coming up with an algorithm for it, which is actually what's going to take more effort this class. Yeah, in fact, this statement here is actually not the end of the world to prove. It's maybe one page and it's an induction argument. But we won't do it that way because I want to prove the stronger one was the algorithm, which is many pages. Okay, so, all right, so we're computer scientists. We want an algorithm. So at some level, the original formulation, which was just events and this dependency structure, didn't really have enough concrete stuff to work with to make an algorithm. It's not even clear how to define an algorithm. Okay, so we have a slightly more concrete setting where we're now going to assume that everything is driven by an underlying set of variables. Okay, so I'm using V to denote some set of variables, a finite set of variables. Okay, so in some probability space where each of these variables is initially independent from coming from some distribution of its own. Okay, and each event is determined by some subset of the variables. So for AI, I'm letting Si denote the set of variables that determine AI. Okay, so for example, in the case that the variables correspond to the actual variables in a formula and whether we assign them true or false. So that distribution was just 1/2 for each. Okay. And each clause corresponded to an event AI, right? So AI was the clause not being satisfied. And then that corresponding subset of variables will be the variables that are in the clause. So now we're going to write that AI and AJ depend on each other whenever they share underlying variables. Okay, so we have events, we have like a finite set of variables, whatever the values of the variables are, you can think of them as bits, for example, but they might be something else, that determines whether or not each event occurs. Each event depends on a limited subset of variables. Okay. But these variables give us something more concrete that we can actually define an algorithm over. So if we generalize the resampling algorithm, we'll get something like this. So in step one, we'll sample all the variables from their respective distributions, whatever they are. And as you know, so the variables, you flip coins, they come up heads or tails, right? And that means some events occur and some events didn't occur. Our goal is to have none of the events occur. So while there is an event AI that occurred, so to speak, we're going to go to the variables that underlie that event and we'll resample just those variables. This is completely analogous to what we're doing with KSAT. So before some clause was unsatisfied, that's a bad event. I wish that didn't happen. So I go to the variables underneath the clause, I resample those variables. That's exactly what's going on here in more abstract terms. Yeah. Absolutely, absolutely. Yeah. So there's a bunch of variables. Each event uses some of the variables, but they can certainly overlap. Yeah. Each variable may be in many clauses, although of course we're going to assume that each event has some limited dependency amongst others. So if it was symmetric LLL, we're saying that, at some level, each event can only overlap with D other events for that value of D. Yeah, which is one limit on the number of events can contain a single variable. Okay, but again, a pretty simple algorithm. Okay. All right, so it's only in 2010 do we come up with this second algorithmic part of the theorem. So 2010 is relatively recent by theory terms, probably relatively old by your terms. Anyway, so under the conditions by which it is possible for none of the events to occur, the resampling algorithm will, in fact, find some kind of configuration of variables by resampling that make sure none of the events occur. Okay? Completely analogous to KSAT, and we can even get a relatively tight bound on the expected number of times we'll resample sort of each event, so to speak. All right. Okay. All right. So, any questions? Because then we're going to start the proof, and the proof is not as nice as the theorem statement, which is already not nice. All right. Talk a lot. I don't know how they came up with this, but it's going to be a lot of moving parts. Okay. So I've got the sampling algorithm in the top right, and then the theorem underneath. So it's going to be some very subtle argument, but we're going to have to kind of create some devices to help us analyze this thing. I mean, I think a priori, it's completely unclear how to analyze this resampling algorithm. I mean, the Lovász Local lemma already is quite mysterious in its statement. I mean, I think it's maybe one of the more mysterious things we've analyzed in terms of just looking at it and like, what the hell is it? Okay. All right, so the first character is we can always associate with a particular instance of the resampling algorithm a log, where I just write whenever I resample an event, I just write down the name of the event, write down the name of the event, so I can log and keep track of all the events that I've resampled. These aren't necessarily all the events that are like ever failed. These are just the ones that the algorithm goes through and tries to correct. There may be events that show up that are bad, and before you even get to it, it gets fixed by some other resampling. So those aren't necessarily included in the log. So the log is only recording the events that are resampled in the order they're resampled. A particular event may occur multiple times in the log. That can happen. Okay, simple enough. All right, that's the log. The second one's more eccentric. It's this notion of witness trees. Okay, so first I'll just start with a definition, and then we'll integrate it into the log and how it comes up. So a witness tree is going to be defined as a rooted tree where the nodes are labeled by events. That's it. Okay. Labels can repeat. Okay. Simple enough definition. Now, okay. This is where it gets a little more complicated. We're going to, come up with this. We're going to study this particular way of taking, say, the first two events that occur in a log and turning it into a witness tree. Okay, so this is a procedure that transforms some prefix of the first 10 or 100 events in the log into a witness tree. And then we're going to do some weird counting stuff with the witness trees. So let me explain. So, okay, so let's say you're sampling the first, you're looking at the first I events in the log. So the last one is A sub I sub I. Okay. So what we're going to do is in step one, we make that the root. Okay. Of our tree. And then we're going to process the events backwards. So we'll go to A sub I minus 1. Okay. And then we're going to look at it and we'll say, okay, look, if A sub I minus 1, that next event, shares a variable in particular with this, because that's the only node in the tree at this point, then I'll make it a child. Well, it's hard to see. I should say I minus 1. Okay. So if it shares a variable, I'll make it a child. If it doesn't share a variable, I'm just going to throw it out. Let's say it shared a variable. Then I'll move to that I minus 2 event. Okay. And then I say, okay, does this share a variable with either one of these? If the answer is yes, I'm going to pick whichever one is lower and shares a variable. So if it only shares a variable with the root, then it'll be a child of here. If it shares a variable with both, I'll make it a child of the I minus 1. Okay. So we just go through and we check to see if there is some node in the tree that sort of overlaps with the event that we're currently looking at in terms of the underlying variables. If there is, we'll choose the node that's closest to the bottom of the tree of maximum depth and make it a child. Okay, seems a little bit eccentric, but it'll work. That's really the best explanation I have for many of our devices is that it'll work and prove something that's quite hard to prove. Okay? In fact, I can't think of, there's other proofs, but they weren't easier. Okay. All right, so that's this sort of process, but I think what's clear is that, whatever, it's clear how you can, any prefix will generate some kind of tree. At the very least, the root of that tree will correspond to the last event in the prefix. Okay. All right, so I guess I set up this example to walk through. So this is like for 3sat or something. And let's say the events correspond to not satisfying this clause or not satisfying this clause. Okay. So if we're to execute this construction on this log, where this is supposed to be the first entry, and then that should be the last entry in the bottom right, we would start with this x1 or not x2 or x4, right? So this would become the root. Okay. Then we move on to this second one, which should say not x2 or x3 or x6. Instead, there's commas. Please forgive me. I guess I can correct that. Okay. And okay, do I add it to the tree? Well, I do because it shares x2. Okay, so I guess I'll put it there. Next, we'll move on to x1, x4, x5. Okay. Where does it go? Well, it shares a variable with the root, but not the other node. So that makes it a child over here. That's the lowest one I could find. Okay. All right. I think you guys get it. So I've messed up this one too. All right, but let's say if you have x7, not x8, x9. Where does this go in the tree? It doesn't go in the tree because x7, x8, x9 is not there. All right, what about x2, x5, x6? Okay, so this is going to go. So shares variable was a bunch of these, but yeah. Okay, so when there's a tie, you can just break ties arbitrarily. It doesn't matter. Okay, and then the last one, x1, x2, x3. Does it go in the tree? Yeah, all the way at the bottom, like that. Okay, so whatever, simple example. All right, so that's how somehow we associate prefixes in a log with various witness trees. Okay. Let me make one observation about this construction that'll be very useful later. All right, so let's say that I'm looking at the first L events, and I'll let T sub L be the corresponding witness tree. Okay. And then suppose I'm looking at two entries in the first L, say Aij and Aik. Okay. And suppose they share some variables. Okay. The claim is that if Aik is in the tree, then Aij is also in the tree. And moreover, Aij is going to have greater depth further down than Aik. So that makes sense, right? Because we're processing things from end to beginning. And if I go to Aik and I put it somewhere in the, this is a bad picture, isn't it? Okay. If I put Aik somewhere in the tree, right? Okay, it's somewhere in the tree. And then later on, we're still going backwards through the events. I get to Aij. I'm asking, does Aij go in the tree? Well, at the very least, it shares variables with Aik. So in sort of the worst case, it'll be a child of Aik, but maybe there will be some other nodes and it'll be even lower. Okay, so nothing too complicated, but this is actually the one critical property we're going to need later about this witness tree. Okay. Again, everything seems eccentric. Yeah. Yeah, so we're just going to consider they share. So yeah, so for simplicity, in the case of case out, I'll just say if they share variables, even if it's negated or not, they overlap. Now, if you look at it very carefully, then you'll notice that if they have the same symbol, then one can't really hurt the other or something like that. And so you can get a slightly better bound, but that just kind of requires making the definitions more complicated to do it that way. So we're just going to say if they share any variables at all, then we'll say that they're related. And it is true that for certain applications, you can look a little bit closer and give a slightly stronger, more refined definition of what it means to have a tilde between them. And that's fine. But yeah, so for simplicity, we'll just say that yes. Okay. All right. Okay. Questions? Sometimes questions are good too, you know. Okay. Like not quite no questions is not good. All right. Okay, so now let's go back to our theorem. So those are the main two objects we're going to introduce and use. Okay, so let's fix an event AI. And remember the theorem stated not only do we find a satisfying assignment, but we can actually bound the number of times we expect to resample each event. So we're just going to fix AI and try to analyze the number of times I resample AI in expectation. If I can show it's finite, right, and that holds for all events, right, then the algorithm will terminate in an expected finite amount of time. And it can only terminate if it successfully finds an assignment, in which case we also prove the mathematical portion, the existence portion of the theorem. Okay. All right, so I'm letting W sub I denote all witness trees rooted by AI. So I just mean like any tree you can think of. So any tree where you make a tree and you label it with events as long as the root has AI. Okay, so that's an infinite size family. Okay. And for each kind of iteration, j equals 1, 2, 3, 4, 5, I'm going to let T sub j denote the witness tree that comes from looking at the log of the first 5 events. Right? So the first 6 events is going to give a different, some witness tree. The first 7 witness events going to give some witness tree. You know, the root is generally going to differ. Right? Okay. All right. So, all right, we want to analyze the expected number of times AI is resampled. In terms of the logs, that's the number of times the AI appears in the log. Okay. All right, so this is at least a little bit more concrete than what we started with. And now here comes sort of, I think, an interesting step. Okay, so every time AI appears in the log, the corresponding witness tree we create, so let's say AI appears in step 10. Then that 10th witness tree, looking at the first 10 events, is going to be some witness tree with AI at the root. Okay, so every time AI occurs in the log, we get a witness tree with AI at the root. So I can take this and I can write it out somewhat bizarrely as, okay, I'm going to go over all the iterations, iteration 1, iteration 2, iteration 3, and I'm going to sum over all the possible trees rooted by AI and ask, what are the odds that the witness tree from the 10th iteration is this particular tree? So the sum of these probabilities will give you the probability that AI appears in step 10, or step J in general. And then summing all up will give you the expected number of times AI appears. Okay, so it's sort of bizarre, but it sort of draws our attention to this kind of question. Okay. All right. Okay, so here's a lemma. So let's say that Aij, that I have 2 indices j and k in the log. Okay, and I want to just first make the relatively simple claim that the corresponding trees have to be different. Okay, so the log looks like, AI1, so forth. Somewhere we get Aij, and then Aik. So I'm assuming that j is less than k. Of course, otherwise we could switch it. So the claim is that the tree that's produced from looking at the first j events must be different than the tree that's produced from looking at the first K. Okay, why? Okay, so if the trees were going, yeah. Okay, so yes, if the trees are going to be the same, then certainly the events have to be the same, or they'll have different roots. So let's assume that aij is equal to aik. Yeah, that's right. So let's see if I can come up. Okay, so let's say that TJ, includes aij and it includes some of these other events, right? Just based on these kind of connections that arise. Meanwhile, TK is definitely going to include aik, and then it's going to include among others aij, and then consequently, once aij is there, it's going to get all of these, right? So you're going to have some aik. Who knows what else is going on? You're going to get some aij, and then you're going to kind of, it could be in different places, but you're going to get everything else from TJ somewhere underneath. So you can already see then that the tree for aik is bigger by at least one than the tree for aij. Okay? Not too complicated. We just have to understand how these trees are made, and then it works out. Okay. All right. So that's just a lemma. So if I go back to where we left off, we had sort of this eccentric nested sum. I could at least simplify it to a single sum. Okay. So now we know that all the trees are distinct in the log. In particular, if a tree appears here, it can't reappear anywhere else. So, if I had interchanged this sum, this would be summing over all j's. What are the odds that a particular tree appears in iteration j, but it can only appear in one of the iterations. So that would collapse to the probability that you produce this particular tree in any iteration, since it can only appear in at most one iteration. Okay. And now here is something that maybe we can analyze. Okay. Okay, so we've analyzed that, or we've gotten to that point, and now we have this somewhat more focused question. Fix some tree T with root AI. What are the odds that it shows up anywhere in the log? All right, we're making decent progress, I think. It's 5:45, right? Okay. All right. Here's the next claim. Okay. So T was labeled by a bunch of events, right? And all those events happened with some probability. Different probabilities for each event if you had a completely independent sample. Okay. Multiply everything together, and I'll call that P of T. So I don't know if the font's too small, but I'm taking the product over all the labels AJ of T with multiplicity. So if an event occurs 3 times, I'll be multiplying that probability in 3 times. Okay. The claim is that this gives an upper bound for a probability that the T appears in the witness tree, in the log. This is probably the hardest lemma. Anyone want to take a bizarro guess at this? how to start a proof. So your last chance to guess, because once I show you a proof, you'll never bother to try again. All right, let's see what's on the next slide. Okay. Again, another wild and crazy step where we have to introduce something out of nowhere. Okay. So to set up the proof, we're going to introduce this, I guess, a procedure for T, which we'll call checking T. Okay. And what checking T is going to do is the following. So I have some tree, okay, of events. And I'm going to process the events in order of greatest depth to lowest. Okay. So that means we'll start from here. This will be number 1, and maybe this will be 2, 3, 4, 5, 6, 7, 8, some kind of like reverse breadth first search or something from the root. Okay. So for each event, maybe starting from the bottom event, this is some event. I'm going to sample the variables underneath and see if that event occurs. If it does, I survive. If it doesn't, I fail. Then I go to the next one from bottom up. I sample the underlying variables, see if I succeed. If I do, I pass. If the event doesn't occur, then it fails. And so we go through all the events from bottom up, and I want to make sure all the events occur. Remember, this is slightly the opposite of the theorem. The theorem wants none of the events to occur. But to pass this check, all the events have to occur. Okay? At a high level, we're going to, in a moment, kind of sync this up with what happened in the log. But at some level, the log is listing all these events, right, that we resampled. Right? So the log has all these events we resampled, which means at the point in time that I resampled it, the event had occurred. The event had occurred, and that's why I resampled. The event had occurred, and that's why I resampled. The event had occurred, that's why I resampled. At a high level, going from bottom up is sort of like going from the beginning of the log to the end. Not exactly, but somewhat correlated, right? Because we know the end of the log is at the root, and each time I try to put events as low as possible. When events are out of order, they're not sharing compared to the log in the tree, they're not sharing variables anyway, so it's kind of safe, so to speak. So on one hand, in the log, I have all these events that occurred. That at some level shouldn't have occurred. They're relatively low probability events, but these are all events that occurred. And here in this check, I'm asking all the events to occur, almost as if I was resimulating the log, although slightly different. I'm only paying some high-level intuition, and we'll make this much sharper in a moment. Okay, so let's check. It's a randomized procedure where I go through the events in bottom-up order, and I pass if upon resampling all the events, all those events happen. Okay. Again, seems obscure at the moment. Okay, so what are the odds that I pass all the events? Well, that's exactly these probabilities that were in the lemma. Okay, so I have to pass the first event, the second event, the third event. They're all independent, so I just multiply the probabilities together. Okay, so it's the product over all the labels in the tree with multiplicity, the probability of those event labels. Okay. So the real claim is that the probability that a particular tree arises somewhere in the log is at most the odds that checking that tree would succeed. Okay. All right, any ideas of how to prove this? Okay, so what we're going to do is, at some level, we have two randomized processes, right? We have all this randomization that generates this log, and we have all this randomization that processes this tree. and sees if it survives. And what we're going to do is we're going to sync them up by using sort of the same underlying randomization. So I want to use sort of the same samples for both processes and show that if one succeeds, the other one succeeds for that fixed sample. So it's a bit delicate, but the high level idea is sort of crude. Oh, we'll just use the same underlying bits for both. Okay. So in that case, what does that mean? So, okay. All right. So imagine generating all of the samples for all of the variables ahead of time. Okay. That could be infinite, and that's fine. If the idea of infinity makes you queasy, imagine we just make a billion variables, okay? And instead of proving the claim that Tj equals T for some J, we'll instead prove the claim that Tj equals T for some J less than equal to a billion, okay? And then at the end, we'll take the limit of billion goes to infinity. Okay, so that's how you would formalize it. Or if you don't care, then just imagine we generate all infinity ahead of time and don't worry too much. Okay? The point is, imagine we had done all the samples ahead of time. Okay? So you have this sort of fixed set of samples for each variable. Right? We need many samples because we're resampling over and over again. And now I'm going to imagine using those samples, the same set of samples for both algorithms. So the resampling algorithm initially is going to use everything from the first column. Okay? And then it's going to choose some event that it wants to resample, which has, I don't know, 10 variables, and it's going to choose those from the second column in that case. That next event, it has another 10 variables, and for each of those variables, it'll just use the first unused sample. So that's either going to be in the second or third column, and so forth. Okay, so this is just a big stack of samples, or queue of samples, whatever. Okay, but it's a fixed order of samples for every variable. Okay, makes sense? Same with check. So as check is processing events from bottom up, whenever it needs a variable, it'll just use the first unused one. Okay. All right, so how are we going to do the mapping? Okay, so, all right, so let's say that the log, lists the events AI1, AI2, AI3 in that order. Okay. Now, every time, look at the first event, right? And the first event, I can associate two different samples with it. I could associate, because we're going to resample and that gives me a new set of samples, right? Or for that first event, I can look at the existing values for that event. Okay, which is in particular is a set of values that made this event occur. So sort of a bad set of values. That's the set of events I'm going to occur with each entry. Okay, so hopefully I wrote it down. All right, so I'm going to map each of these AIJs to the sort of the values of the corresponding variables that had caused that event to occur at that point in time. So that's kind of going backwards. Okay. Right. Okay. So in particular, event one, the first event, is going to be drawing on samples from column one because it's definitely using things from the initial step. Event two will be using samples from, or will be mapping to samples from column one or column two. Okay. So again, for the case of the events in the log, I'm going to sort of have them correspond to the events that caused the sample that caused that event to be resampled. So it's going backwards. T is going to be a little bit more straightforward. So for every event in T, I'm just going to associate it with that actual sample it uses when it checks that event. Okay. Now, okay, so, all right, so let's say that T arises in the log. I want to show that check T passes. Okay. So T arises in the log, and I want to argue that sort of the sample that I'm using for each check will pass the event. Okay. And again, the high level idea is, let's say that AI1 turns out to be the bottommost event in the tree, right? So at some level, that AI1 up here is going to map to a sample from the initialization that forced AI1 to be resampled. So that was a bad sample, so to speak. And if that would also be used by checking the event in the first iteration, and it'll pass, so to speak. But you have to be a little bit more careful. To the general one. Okay. So, all right. So the checking procedure is in the bottom right, right? So remember, we process each event in decreasing order of depth. So from bottom up, and we try a sample and we see if the event occurs, and if so, we keep going. So you want the events to occur and check. All right. So let's, for every node in the tree, was label AJ. So I have a tree, right? And I have my node here, which corresponds to event AJ. Okay? So for every, that's not great. All right, there's two J's going on. Sorry about that. So for every variable that underlies this event that I'm looking at right now, I apologize that there's two XJs. Entry E is going to use the H's sample of XJ, where that's the number of entries in the log, including E, that uses that variable. Okay, so we have to be careful about this. There's some fence post error. So I'm looking at, so I have a node in the tree that corresponds to an entry in the log. So, and then I'm looking at some variable that is used for that event. Which sample do I use? Do I use the first sample, second sample, third sample for that variable? Well, it's going to be exactly how many other events are in the log using the same variable plus this one. So less than or equal, so to speak. So it's going to use the H sample, where H is the number of entries, including E, that use that same variable. Okay? And I wanted to argue that check T is going to also use the H. I don't know how to do this. I know how to do ith and kth, so I don't know what H is. Okay. The number H, I want to argue that sample, when I process that node, will also use the index H sample of this variable. Because then it'll be using the same variables, the same sample of variables that put the event in the log. And it's only in the log because the event occurred. So it'll pass the check. Kind of makes sense? Well, you have to believe me. We're in the 15 minutes left, which means as class progresses and it gets closer to the end, you have to believe me more and more. This guarantees, by the end, that we finish all proofs, because there's no limit as we approach end of class. You're just happy to accept anything, and I can just go to the end of the presentation. Okay. So remember this earlier observation about our witness tree construction. Okay. The only real claim was that, whenever I had two events in the log that shared variables, if this event was in the tree, then this event will be lower. Okay. So let's go back to our case from before, right? I had some event in the log, which had some variable. Okay. And maybe there's 10 other events in the log that use the same variable. So this is number 11. Okay. So in the tree, right? This will be in the tree because we're assuming it's in the tree. And those other 10 will also all be in the tree. And moreover, they'll all be below the tree, in the tree. So that will use the first 10 samples of that variable, and this will be number 11. Anyone else can't show up before because that's like the contrapositive of this observation. Okay, so there's like a very, very delicate correspondence that shows that if this event is event number 11 using this variable, then it's also going to be the 11th lowest event in the tree using that variable. Okay, so you end up getting this exact correspondence. Okay. And again, now this event that uses that variable, for all the variables that contains it, those variables cause the event to be put in the log, right? That sample of variables corresponding to the event put the event in the log, which means in particular that set of variables induces the event. That means when check comes around to using the exact same sample of variables, it'll say, oh, the event does occur, and it'll pass the check. Okay? So by this very delicate mapping, where we sort of fix the underlying thing and we see the log that comes out of it and the corresponding tree, and we check the tree, we see the tree has to pass the check. Okay. So if you put everything together, what we've shown is that if we kind of run everything on the same set of samples, if the log induces a particular tree T, then checking the tree will also pass with that same set of random variables. Backing up further, we already know it's much easier to show that the probability of checking succeeding was this product P of T. And now we know that the probability of T occurring is at most the probability of checking, because if T occurs, then check T succeeds. Okay, it's kind of crazy, but it works. Okay, questions? All right, backing up further, where do we stand? We're almost done. Okay, so, all right, so WI was a set of all witness trees with the root AI. TJ, again, was that J's tree, J's entry in the log. And we have sort of reduced the expected number of times that AI is resampled, that's what we're trying to bound, to now this product of kind of probabilities in T. So all we got to figure out how to do is sum up all of these PFTs in WI. The claim is that it's at most XA over 1 minus XA. It should be XAI. Okay. Okay. Somehow we're going to prove this wild thing. Okay. But that'll give us the claim, right? Because the expected number of times AI is resampled is already at most this sum, which then is at most this, and that's whatever we had originally claimed. Okay, so we really are almost done. Okay. All right, guys. One last chance to do some guessing. How can I prove this final claim that summing over all trees with root AI is at most x of AI minus over 1 minus x of AI? Yeah. Well, no, we can't use it yet because we're trying to prove it. But it is true that we are finally at some point in this stage going to use this thing that has not come up to this point. Okay. Yeah, so that's going to come up. We have to do, yeah, we will, but we're going to have to do a little more work. Okay, well, we're going to bring back an old friend. And somehow, this is going to come from analyzing a certain Galton-Watson tree type of process, a little bit more eccentric than what we previous had, which was more symmetric. Okay? Somehow we're going to relate P of T to this crazy thing. Okay? All right. So this is going to be, so Galton-Watson trees generally refers to any kind of tree thing where children come out with some process and stuff like that. Before we had only analyzed these very simple cases of like K children was probability 1 over K. But, you can analyze any complicated thing, and I guess you still call it a Galton-Watson tree at the end of the day. So, we imagine creating a tree from the following experiment. So in round 1, you always add AI. Okay? And in the next round, for every event AJ, where AJ is overlapping AI, okay, I either add it or I don't. The probability I add it with is XAJ, so the probability I don't add it is 1 minus XAJ, and there may be several children, okay? And so we kind of keep going. So in the third round, I'll only be adding events that share variables with AJ. Okay, so we sort of keep creating a big tree where each child shares variables with the parent. And the probability of an edge appearing is governed by its X value. Okay, so maybe the process terminates, maybe it doesn't terminate. Okay, all right, so, oops. Let's fix a particular tree. Sorry. And I want to ask, I left somebody behind. Let's fix a particular tree and ask, what are the odds that this process produces that particular tree? I'll let Q sub t denote that probability. We're going to analyze that first. Okay. How am I doing? Oh boy. Okay. Okay. We'll have to go a little bit more quickly. Okay, so here's how we're going to do it. All right. For every node in the tree, I'm letting a sub n, node n, I'm going to write a sub n to denote the corresponding event. Okay. And for every node, it has some events that are children and it has some events that were left out because those were the odds, right? So B sub n denotes the events that could have been children but weren't, the disappointed children. Okay. All right, so if I just wanted to first estimate QT, okay, then, for every node in the tree, so I'll just write n in T as kind of the node n in T, right? Except for the root, we'll address that in a moment. There was this probability that it was created as a child, right? So for a fixed tree, I'm going through all the nodes and saying, oh, these are the odds that this node, came up as a child of the parent. Okay. We also need, since that doesn't hold for the root, I have to divide out the root because the root's automatically there. So the root doesn't have to pay this penalty. And then for that node, if I go through all of the disappointed children, or the ones that it doesn't matter. Okay. All right, so these are all the events that were left out. I would have told you a funny story, but we don't have time. Plus, it wasn't very funny. Okay, so I want to simplify this. All right. And what I'm going to do is, and I'll explain this in a moment. Okay. What I'm first going to do is I'm going to replace this inner product. So the BN's a little bit ugly, so I'm going to get rid of it. I'm just going to go over all events AK that are related to AN. Okay. Okay, so I've gone from the events that were omitted to now just all the events. Okay, including the ones that actually became children. Now the ones that actually became children appear as a node elsewhere, with the exception of the root. Okay, so we can divide that out, 1 minus XAN. Okay, so this will divide out the extra terms that were introduced. Okay, except we're doing one too many, we're doing an extra division for the root that we shouldn't do. So this becomes 1 minus X AI. A little wild and crazy, but it works. There's no time to challenge me. Okay, so this is looking a little bit cleaner, right? And now I can take each of these terms, right, and kind of sort of subtract it out from the corresponding one of its parent. And that'll give me 1 minus X AI over X AI product over all nodes X A N product A K A N 1 minus X A K, except in the product I now get to omit A sub n. Okay, it's working, I promise. And I only note that this starts to look a lot like this, in particular including this last part. Okay, great. Almost done. This is the part of the class where I have to keep insisting we're almost done. Okay. All right, so I now want to analyze P of t. Okay. And this is the product over all the nodes in the tree, probability of the event occurring. Okay. Finally, at long last, we're going to use this bizarro thing. Okay. So this will give me the probability over n and t. Okay. Let's make sure I do this right. X, A, N, the product as AK over all other events that are related, except not including that event, 1 minus X, AK, right? Which is exactly this part up here. So this is equal to, if I invert the thing up above, xi divided by 1 minus x ai times q of t, where q of t is this big thing, right? This was q of t. Okay. Is that okay? We're only one line away. Okay? I'm going to let you guys have the kill shot. All right. So, finally, our goal was to bound over all trees with root ai p of t. Okay? And we now know this is at most, sorry, this should have been a less than equal to. This is at most xai over 1 minus xai, summing over all the trees with root ai, q of t. That's okay, right? Okay, we're almost done. What's the last step? In particular, I want to get rid of that sum over qt's. How do I annihilate this sum? What does q sub t represent? So q sub t represents the probability that the Galton-Watson tree process we described produces t in particular. Okay? So now I'm going to sum over all t's. Starting here. 1. Why 1? Well, we only produce one tree. Right? So the probabilities all sum to at most 1. Okay, and that was the last step of our proof. We zoom back out. That's what we need. Oh, that's what we have. That's our last claim. You put everything together, and somehow we've shown that this unbelievable algorithm works. Okay? So now you can solve KSAT. You can do a lot of other stuff too. I'll try to add more examples to the notes so you can see how rich LLL is. I didn't do a great job in that aspect. Okay? All right. Okay. Thank you.